something I can, guiding model-driven combination dose selection using multi-objective synergy optimization. Thank you, Jana.
Thanks, Kathleen. And well, thank you for being here. Siv, thanks for welcoming me into the family this week, which is when it happened, but I do appreciate it. And the time I've spent with your students over the years has been great. So the project I'm going to tell you about today is something I worked on during my sabbatical. It was in 2022-23, and I spent the sabbatical at EMD Serono, which for those of you who don't know is Merck, but German Merck, not American, North American Merck. And so the group I work in is translational quantitative pharmacology. And like Colin's talk yesterday, I was really interested in the question of first-in-human dose projections. And I came in, I'd say, as an academic consultant trying to help them sort of improve some of the methodologies they use. And this is joint work with Irina Kareva. So let's get this working. Okay, that didn't do it. Yeah, that's what I'm going to do. And then it wakes up. OK. So the particular question we were interested in is designing safe and effective combination therapies. And there's really two different ways you can think about this question. I'll just tap on the slides. OK, so the first question is, what makes the best drug combination? That is, you might have a set of N drugs. You want to look at their behavior together and identify the best ones to combine. A secondary question is, right, and then you might want to choose this one because it has the best effect. But a second question is that of a dose and schedule selection. If you already have two drugs that you'd like to combine, what is the best way to combine them? Now, this is the question that comes up more in the pharmaceutical industry because you already have a standard of care. You have a new drug you're trying to bring in, and you want to combine your new drug with the standard of care. But here I'm being sort of intentionally vague when I'm using this word best. What do I mean by best combination in either of these contexts? So synergy you often see used as a pretty compelling metric for trying to combine drugs, because what synergy does is either quantify the gain in efficacy or the reduction in toxicity that you see only when two drugs are given together. Now, this is often shown schematically in the graph here, where you have this line of additivity. And if you have more effect than what would be anticipated through additivity, we would call it synergy. That's often simplified as saying 1 + 1 is greater than 2. And on the other hand, if you have 1 + 1 being less than 2, you call it antagonism. This all sounds really simple until you realize that the definition of additivity has been, and I quote, at the center of controversy amongst leading researchers in the topic for the last century. That is, no one agrees what additivity actually is. And if you don't know what additivity is, you then don't know what synergy is. So the reason is, and I'm going to give sort of a toy example here, is that additivity does not simply mean adding effects. So in this toy example, say you're measuring % inhibition of cancer cells, and one drug kills 60% and another kills 50. You're certainly not looking for a 110% kill at an additive dose, right? So it just shows here, and there's reasons this is a toy example, but that adding is simply not a metric of additivity. And as mentioned, there's an overwhelming number of divergent definitions of additivity in the literature. So what I thought I would do is step back from drug combination for a minute and just try to think of the language of synergy. So it's going to seem weird, but play this game with me. Here's the scenario I want you to consider. Two people, they're painting a room together. Person one can paint the room, 40% of the room in 3 hours. Person two can do the same thing in 4 hours. And I want to think about what synergy means to you in this context. So there's two ways you can think about this question. The first is you can think about how much of the room actually gets painted. So say person one puts in their 3 hours of work, person two puts in their 4 hours, and then you look at it and they painted 25% of the room. I think we'd all agree something went wrong here, right? Maybe person one knocked over person two's paint can, but I think there's no question something antagonistic happened in this working relationship. And then say they painted 100% of the room. I think we'd all clearly agree something good happened, there was synergy. But what if I said to you 60% of the room was painted? I think the classification becomes a lot less clear. And that's only one way of thinking about the problem. You could also think of how much effort went into painting the room, which in this case would be the time spent painting. So suppose they're looking at that 40% target and it took 10 hours of work. No question that's a problem. Individually, you could have done better. That's antagonism. Okay, it took an hour. We'd all feel really good at synergy. What if it took 3.5 hours? Again, really not clear how you would describe that. So what I mean to illustrate with this example is that when you see extreme cases of synergy and antagonism, you know it. The problem is additivity is one line in an infinite space somewhere in between those points. Where does that point lie? And people don't agree on where that point lies. And it has important consequences that I'll talking about. So if you look in the literature at existing additivity metrics, you'll find them divided into two categories, just like in that painting example. So first, you can think of the output of a combination therapy, which in this case would be the efficacy of the treatment. The oldest metric of additivity for efficacy is the notion of Bliss additivity. Bliss additivity simply follows the formula for mathematical independence. So it's literally the probability of the union of two events under the assumption the two events are independent. So it scales efficacy to a value between 0 and 1 and says additivity is the line where independence applies. Another metric used is highest single agent. This is a much lower bar for additivity. They say you achieve additivity in a combination if the combination is as effective as the more effective monotherapy. So any better than you do than monotherapy, you've already crossed into synergy territory. So they're very different metrics of the same thing. And that's only if you think of output. But if you think of the painting example, there's also the input. So how much time went in there, but from the perspective of drug combination, this is going to be the potency of the therapy. You can think of this as how much drug you've administered related to toxicity. The oldest metric here is that of low additivity. Low additivity assumes that you have parallel dose response curves with your two drugs. And as a result, you can always convert from a dose of drug 1 to a dose of drug 2 with a fixed scaling ratio that gives you the same efficacy. Bliss and low people have been fighting for 100 years. In the 1990s, they convened a conference where they were going to decide on one metric, and they left more angry with each other than they started. So these are the oldest two metrics. And to make matters worse, we decided to introduce the new metric here in the potency category. And this metric here is really meant to be an analog of highest single agent, but in the potency category. So you identify the more potent monotherapy. That's the line of additivity. Any more potency in the combination, which means less drug, would be synergy. Now, when you have different metrics, you need a way to compare across them. So people use the combination index, not confidence interval. I apologize for that as the notation here. And the combination index is defined as follows. 1 is normalized to mean additivity. Less than 1 is synergy. The smaller it is, the more synergistic you are. Greater than 1 is antagonism. Okay, and I do want to note, though I won't go through these, there are many other recent papers in the literature attempting to define this line of additivity. And maybe having so many definitions is not a huge problem until you start to realize, well, they're used very inconsistently. And as this is not my quote, someone in 2019 noted, the metric people use in the literature appears largely arbitrary. They just pick one because they found it used before and they use it. Maybe not a problem until you realize that the metric you choose results in it's completely sensitive to the predictions that get drawn. So a recent meta-analysis found that based on the metric you chose, you may take the same combination and call it antagonistic or synergistic, right? So this is a huge problem if you're trying to optimize synergy. So that being said, synergy optimization is a hard problem. It has a few ways to be defined, and we wanted to try to tackle this since synergy seems to be a way people like to think about designing combination therapies. So the approach we're going to introduce is a multi-objective optimization framework where we think about optimizing both synergy of efficacy and synergy of potency. So for those who were around last week, one of the groups was thinking about toxicity in treatments, and this is a way to think about toxicity because synergy of potency gets at that question. I want to note this is sort of in the spirit of prior work by Carlos Lopez and colleagues on what they called the music method. They were thinking about efficacy and potency, but not for the combination of the question of dosing and scheduling, but for the question of identifying combination partners. So our method is similar in nature. We've named it MOOCs-DS for multi-objective optimization of combination synergy dose selection. So let me tell you a bit about multi-objective optimization, and then we'll apply it. So in this case, you want to think about having objective functions that you want to simultaneously optimize over your decision vectors. So to make this super concrete, your design space here would be your set of allowable doses. And your goal might be, forget synergy for a moment, to minimize both tumor size and toxicity. Now, this might be subject of a little bit of debate, but let's just say in vitro as an example, if you want to minimize tumor size, you should probably give as much drug as possible, at least in the short term. But if you want to minimize toxicity, well, you shouldn't give any drug at all. So obviously, these objectives compete with each other. And when you have competing objectives, the question becomes, how do you solve these multi-objective optimization problems? There's more than one answer to this question, but we're going to use the notion of Pareto optimality to do this. And we're going to do it by taking our points in design space first and mapping them over to the criterion space, which is the value of your objective functions. So the way this works is as follows. You take a dose in design space, like no drug. You map it onto criterion space. Well, when you give no drug, your tumor size is as large as possible, but you have no toxicity. If you then take the case of giving as much drug, you are going to maximize toxicity, but probably minimize tumor size. Every point you have in design space maps over to a point in criterion space. It is in criterion space that we will perform our multi-objective optimization. So to understand how you do this optimization, what I want to find are called non-inferior solutions, and it helps us see what an inferior solution first is. So this point is an inferior solution for a minimization problem. What is the reason? I can find another point in the space, like this one over here, where both objectives are smaller, so this is clearly not a solution of interest. This point, on the other hand, is a non-inferior solution. What is the reason? Well, I can make objective 1 smaller, but I've made objective 2 larger. And I can make objective 2 smaller, but I've made 1 larger. So this is an example of a non-inferior solution. The set of non-inferior solutions form what we call our Pareto front. Our Pareto front is our solution to this multi-objective optimization problem. Each solution on your Pareto front then maps back into a point in design space. So a dose of drug 1 and drug 2. And it would be up to the user to then decide which point on the front they want, which in this case would be how to balance tumor size with toxicity. Now, if we go back to the question posed earlier, if your goal is synergy optimization, now we have to decide what synergy objectives do we actually want to optimize. So we decided to try not to wade into the debate of the best way to define additivity and said, let's think about several ways we can do this. So the Zoom thing is getting in the way here, but on the top, we're looking at different metrics of synergy of potency. So both low and lowest single dose. So we're going to consider both of those objectives. Get the mouse back. And then we're also going to consider an objective. Don't worry, you can fix that. Thank you. I appreciate it. So we're going to consider synergy of potency as one of our objectives, but 2 different ways to define it. Also, we're going to consider synergy of efficacy using 2 different metrics. Also, right? So we now have, thank you. What this does is give you 4 different criterion spaces, right? Each depending on which definition of additivity you choose for potency and which you choose for efficacy. So we're going to do the Pareto optimization in each of these 4 multi-objective spaces. And then we will compare the output across the spaces and see, do we identify any combination protocols that are optimally synergistic independent of where you drew your line of additivity? So it doesn't sort of matter which definition you use. That's the question we want to ask. So the first thing we decide to do is apply this on a toy model to get a sense of how it works. Then I'll show it to you on real data. So the model, right, very simple, logistic growth, and I'm acting like there are 2 drugs here, right? So the drugs are the 2 kill ones, the linear kill term at a rate D1, the quadratic kill term at a rate D2. We perform our multi-objective optimization in each of the 4 spaces. So for instance, in the upper left-hand corner, we use low for synergy of potency, bliss for synergy of efficacy. Every point you see here corresponds to a dose, a combination dose we tried. If the point is colored blue, it is not optimally synergistic. If it's red, it's an optimally synergistic point. We get the red points in each of the 4 spaces. And then the question becomes, where do those fall in dosing space? So we take all those points and map them back into dosing space. So there's a lot to see here, but each drug as a monotherapy was considered over its 5% to 85% inhibition range. And then the color you see is the efficacy of the combination therapy predicted by the model. If you do not see a number anywhere in that space, that means that dose was never identified as optimally synergistic. Doesn't matter how you define additivity. If you see a number, that number tells you how many times it was optimally synergistic. And what's sort of interesting to note here is, well, first of all, most of the doses fall at the boundary, which to me is almost more boundary effects than biological meaning, because you cut off your domain, right? But also, there are no fours anywhere in this space. So you're getting that your prediction of what is optimally synergistic completely depends on how you defined additivity. So if we sort of look through the process of what we did here, where we have a model, we establish a dosing range, we calculate our combination indices, and we do our Pareto optimization, we end up sort of in this case where we get very inconsistent predictions about what you would classify as the optimally synergistic combination. And we would recommend being incredibly cautious about using synergy as your way to design a combination protocol in this case. To show you why so much caution is needed, I'm going to step away from the Pareto optimization and just show you the combination index using each of the four methods. So the top two are both synergy of efficacy metrics. The bottom are synergy of potency. And the idea, again, is less than one is synergy, the smaller the better. I know the numbers are harder to read, but I'll help interpret here. So when you look at Bliss up here, all these numbers are greater than one. So Bliss is saying everything here is slightly antagonistic. If you wanted to maximize the synergy, so get as close to synergy as possible, you should go into the dark blue regions. Now let's see what highest single agent says, which is also a way to measure synergy of efficacy. Well, it says everything has a combination index less than one, so it calls everything synergy. Maybe not the biggest problem until you say, well, where is synergy maximized? Well, that's this blue region. Well, the region, that blue region, goes through the most antagonistic region that Bliss would identify. So even if you're trying to measure the same thing, synergy of efficacy, you would pick completely different combinations. So it's not just that the numbers are different, it's that the structure of the space is different too. So it's a real problem. And the same thing happens if you look at potency. So if you look at low over here, low wants to sort of be in this upper right region of space to maximize synergy of potency. And LSD wants to be at very low doses of drug too. Totally different structures. So, right, this is consistent with that observation from earlier, right, that the choice of a synergy metric influences your conclusions that you draw substantially. And it's not just the label, but it's what dose you would actually choose. So, as I said, I probably wouldn't want to use synergy as my metric here at all. But for those who insist on using synergy, if you understand your mode of action of your drug very well, you might be able to say if the assumption of drug independence is reasonable, and you could use Bliss. And if you know your dose response curves and they seem to be parallel, you could be more confident using low. But truth is, I would just avoid it altogether. Luckily, this doesn't always happen. So let me show you another scenario. So now I'm going to show you a model with some real data. So the combination therapy we're looking at is the immune checkpoint inhibitor, pembrolizumab, and the anti-angiogenic agent, bevacizumab. So the experimental data that we're going to calibrate our model to is for two non-small cell cancer cell lines, one p53 wild type, one p53 deficient. So the data we have is going to be control growth, growth with the monotherapy of pembro, the monotherapy of beva, and then a combination therapy. So that's the data we have. So we're going to build a model around this. We built a pharmacokinetic model parameterized separately from literature data. We found pembro is best described by a two-compartment PK model. Here you can see the fits of our model to that published data. And beva, which is even an older drug, this data is from 1999, right, was best described by a one-compartment PK model. And there you can see the fits of the model to the data as well. So with the PK calibrated, we move to the pharmacodynamics. So here we're going to assume a very simple model of logistic growth of the tumor. And the cells that are killed by a drug then go through these like 3 different stages before they die. But the only ones that have any real activity are the ones in this X1 compartment. Everything else is just moving through death. And the tumor size is the sum of the 4 compartments. We calibrated this model with the PK fixed to the experimental data. So in the first column, it was the P53 deficient, then P53 wild type. And you'll see fits to control growth, the 2 monotherapies, and the combination therapy. We described the data well. So then we turn to the question, in this setting, can we use our model to identify optimally synergistic drug combinations, doses? So we're going to start with the P53 wild type cell line. So again, I'm doing that multi-objective optimization in the different synergy of potency and synergy of efficacy spaces. Here you see the Pareto fronts. They don't give you much information until you map them back onto dosing space. And here you can see Pembro on the horizontal axis, Beva on the vertical axis. The red star is the dose used in the experiments for comparison. And again, the color is the model predicted tumor growth inhibition ranging from 0 to 1. So that's all relative to the control. So the thing I want to point out here that we didn't see before, and it's probably hard to see from where you're sitting, but there's a line of 4s that run through that dosing space. So what that line tells us is independent of how I define synergy of potency or synergy of efficacy, right? The model is saying these are synergistically optimal doses to consider. So you have a set of doses. What would one do then? Well, then you'd have to consider further. If your goal is just to maximize tumor growth inhibition, you get as much into that yellow region as possible, which of course is going to mean giving more drug. If your goal is to minimize toxicity, you would want to take the lowest one, right, with the least amount of drug. Now, that being said, you might notice that that still gives double the amount of Pembro as the experiments did. That might not be okay. So then you can use this to make a go or no-go decision, right, for this drug, for this classification, which are our wild type population. We did this again for the P53 deficient cell line. Luckily, we still did find that line of 4s going through space, right? So the decision was sort of universal about where you want to be in dosing space. But what's interesting is to compare it to where the experimental dose is, and it actually gives comparable amounts of Beva and significantly less Pembro than was given in the experiments. So if you're thinking of making a no or go decision, this is a good indication that the P53 deficient cell lines could respond very nicely to this optimal combination therapy. So we didn't see that in the wild type cells. So if we go back to the wild type cells, I want to note that when we're doing this optimization, so we're varying the dose, but the protocol, the schedule of the drugs was fixed as in the experimental data. So we don't have to be married to the experimental protocol. So what I wanted to show you is we can expand this method beyond the experimental protocol. So the experimental protocol happened to space the Pembro out by 3 days each dose and the Beva out by 3 days. So we said, let's loosen that. Let's allow Pembro to be spaced by anywhere between 1 and 5 days, and we'll do the same for Beva, anywhere between 1 and 5 days. And what you're seeing here is the set of 25 Pareto fronts in one of the spaces. I don't want to show you all 4 because it becomes a lot to look at. But you see the set of 25 Pareto fronts in one of the multi-objective spaces. Remember, the goal, maximize synergy, means minimize the combination index. So you want to get as close to the origin as possible. And if you look at what protocol does that, that is the 1-2 protocol, which says space Pembro out by 1 day and Beva out by 2 days as optimally synergistic. If then we map back into dosing space and say, well, what doses should we do with that protocol? The X's mark those Pareto optimal doses. And I want to compare that to the experimental dose that was spaced out by 3-3, right? That's where that dose falls in the space. So what I want to point out is we now have Pareto optimal doses that do give less drug. I want to admit we're giving them closer together. So it's not a guarantee we've removed the toxicity issue, but it's a possibility, right, of a protocol that could have a reasonable toxicity profile, but it's still optimally synergistic. So to summarize, right, what I did here was introduce a methodology for identifying optimally synergistic combination doses using 2 forms of synergy, efficacy and potency. Again, my recommendation is that if you have optimally synergistic doses that sensitively depend on that additivity definition that no one agrees on, don't use synergy as your way to design combination therapies. There are other ways you can design them. But if, on the other hand, you do get robust predictions about optimally synergistic doses, right, then this methodology could be a nice way to identify those protocols. So if this is a methodology you'd be interested in using in a preclinical setting, what would you actually need? Well, you need PK for all your drugs, and you need a minimum of tumor volume time course data for 4 cases. You would need a control case, at least 1 case for each monotherapy and a combination. Ideally, you'd have more data than this so you can withhold it to validate your model, but at minimum, you need this to parameterize your model. And then we've made the code available on GitHub. It is in MATLAB, but you could just basically stick your model into it and all the multi-objective optimization will just happen. I will note right now that all of this depends on having tumor growth inhibition data relative to a control case, which is not something you're going to have in a clinical case. So right now, the thing Irina and I are working on is basically being able to expand this methodology to work with clinical data. Right now, it's for preclinical data. So let me just end by acknowledging Irina, who I mentioned, who brought me into EMD Serono for the year, but really the whole team at EMD for welcoming me that year. If you're interested in the paper, you can download it with that QR code. And yeah, thank you all for your time. I appreciate it.